All right, so last week we went over and spent quite a bit of time on conservation of energy. And before that, we talked about work energy theorem. Those two ideas are very closely related. Okay? You cannot have energy to conserve unless work was done to give you that energy in the first place. Okay, so those two things do go hand in hand. Right? What we're looking at in this question is a situation where energy, mechanical energy, is being conserved from one point to the next. No work is being done by the roller coaster. Okay, so if I was standing next to this thing, what would it look like? Or sound like? Or yeah, you wouldn't hear anything. This would be a perfectly silent roller coaster. Because if you could hear it, that would mean it was doing what? Work. And it was losing energy. It would be converting some of its mechanical energy into sound. Okay? And as a result, it would slow down, which is what happens in the real world. Okay? But we're looking at this from a physical, from an ideal physical world perspective. Okay. So what we need to set up here is a law of conservation of energy. So our initial energy is equal to our final energy. We have both types of energy on both sides. Initial potential, okay, initial kinetic, final potential, and final kinetic. Okay. What I'm looking for is part of my final kinetic energy, so I want to isolate that before I put in all the formulas. So I'm going to subtract the final potential over to the other side, which will give me the following. M times G times H initial, so my initial potential, plus 1/2 MV initial squared, so my initial kinetic, minus M times G times HF, my final potential, equals 1/2 MVF squared. Okay. Now, I gave you M, but do you need it? Not in this question, so I'm going to cancel that off. And what am I going to do with the 1/2? Divide it over. Okay, and then what do I have to do? Square roots. All right, so what that's going to leave me with is the following. 9.81 times 40 plus 1/2 times 5 squared, okay, minus 9.81 times 8.5 divided by 1/2. All right, so we're looking at the speed of 25, we only have two significant digits there, so 25 meters per second at this point right here. Okay, how are we feeling about the law of conservation of energy questions? So excellent, okay. Reasonable, they scare the living you-know-what out of me, okay. All right, if that's the case, the good news is you're tested until Wednesday. Okay, you can still come in and get some help from me on them. And we're going to be working on those a little bit still today. Okay, the thing to remember about both work energy theorem questions and law of conservation of energy questions is their pattern. Okay, as long as you can recognize which type of question you're dealing with, there's just a pattern to follow. Every single time I've done a conservation of energy question, I started out with this, and I've expanded to this, and then isolated what it is I'm looking for. Since I was looking for VF, I isolated the type of energy it's part of. Okay, then I plugged in the formulas, then I manipulated, okay, and solved. Okay, it's always going to be the same pattern. The work energy theorem questions are the same. Identify what kind of energy is changing, set work equal to that, isolate, solve. Okay, that's always the same pattern. Speaking of which, see if we can solve that. Okay, so what kind of problem is this one? It's a work energy theorem question. All right, what kind of energy is being changed in this one? All right, so the work is changing the kinetic energy of the ball. Okay, our givens are the mass of the ball, 0.180 kilograms. That's something to watch for. Okay, remember that your units always have to be in kilograms per mass. Okay, the final speed of the ball was 38 meters per second. What do we have to assume the initial velocity was? Right. Okay. And then the distance it was stretched was 0.45 meters, right? So that's our information there. Force times distance will equal 1/2 mvf squared minus nothing, okay, because we didn't have any initial kinetic energy. So I'm solving for the force used, which means I'll divide both sides by distance, okay, and that'll leave me with force. So 1/2 times 0.180 times 38 squared divided by 0.45. Alright, so we're looking at 200, actually we only have two significant figures here, so 2.9 times 10 to the 2 newtons. Okay, how important are units? Really, really important. On that note, I've just looked at a few of the work labs. My graph on the work lab was force and distance, right? If I calculate the area underneath this line, am I actually calculating area? I'm calculating, right. What are the units for work? Yeah, they're joules. They're definitely not that. Don't laugh. I haven't marked one that didn't have that yet. I'm just putting that out there, okay? But I haven't marked one yet that didn't have units of meters squared for that first calculation. Okay? I'm doing them right now. I've only done 2, but that's not Okay, what kind of energy is being changed in this one? Potential energy. Okay, so our givens are force is 400 newtons. Okay, the distance over which the force is exerted is 1.5 meters. Okay, the mass of the ball is 0.340 kilograms, and as we just said, work is changing the potential energy of the ball. Now, where do we assume this is being thrown from? Yeah, from a height of 0. We're not told otherwise. So, okay. Yeah. So we've got m times g times hf, and we're looking for hf here, so we're going to divide both sides by mg to find that. So that'll be 400 times 1.5, okay, divided by 0.340. So this is going to go pretty high. Okay. So 600. Oh, sorry, I forgot. Yeah, the 9.8. Yeah. Okay, so 600 on the top divided by 0.340 divided by 9.81 times 9.81. All right, so we're looking at a height of 100 and actually we only have 2 significant figures, so 1.8 times 10 to the 2 meters. Yep, 10 to the 2. One is proper scientific notation, the other is mathematically writing 18 times 10 to the 1 is okay. That's still 180. But proper scientific notation, the base is always a number between 1 and 9.9. Okay, questions on any of those? Okay. So, I've got a variety of differently worded types of questions here that I want you guys to try here based on both gravitational potential energy, conservation of energy, but they kind of just go randomly, okay? So I want you guys to give these ones a try just because they're different, okay? So you get kind of a feel of all the different ways I might ask either work energy theorem, okay, or conservation of energy. So these are all in the workbook, and they're on page 12 and 13. Okay, so that's the ones I want you guys working on right now, starting on number 6 here, okay, and working through to even these other ones down here, okay, just to give you a good feel of what to expect on Wednesday. Okay, and if you need some help, just let me know and I'll come around and help.